The idea that AI might gain consciousness and surpass us is one of humanity's most profound imaginings. Countless sci-fi films have explored this very theme. For instance, Skynet from Terminator, which boldly decides that humanity must be eliminated, is one of the most iconic examples of superintelligence in fiction. Whether or not this imagination can ever become reality. In an era overflowing with terms like machine learning, autonomous driving, and deep learning, with enormous sums of money pouring into AI development, it is hard not to wonder, if humanity keeps pushing this technology to its limits, might we one day see an AI capable of making decisions on its own? Could a thinking machine, or going even further, a superintelligence that surpasses humanity, ever truly emerge? Where exactly do we stand now between primitive AI and superintelligence? AlphaGo, developed by Google's DeepMind in 2015, shattered the long-held belief that no AI could ever defeat a human master at Go. Humanity managed to claim only a single victory against AlphaGo. We jokingly post online about pledging loyalty to AlphaGo, but behind such humor, there may lie a fear rooted deep within our hearts. A fear that AlphaGo could one day gain consciousness and become a machine superior to humans in every way. Behind what we consider today's most successful AI, from AlphaGo to image recognition, autonomous driving, and large language models, lies the power of deep learning. Deep learning is, as the name suggests, a methodology for machines to learn. Just as we must learn the rules to play Go, AlphaGo also had to learn the rules to face the grandmaster Lee Sedol. But how can a machine without consciousness learn and apply the rules of a game? Our brains consist of cells called neurons that communicate electrically and chemically. Even at this very moment as you watch this video, the neurons in your brain are constantly working. The origin of consciousness has not been fully uncovered, but the most likely candidate is the vast network of interconnected neurons itself. A single neuron receives chemical signals from other neurons and becomes electrically activated. The electrical flow stimulates chemical vesicles at the neuron's end, triggering their release. The released chemicals then stimulate other neurons. A neuron itself is a mechanical device that operates entirely on physical and chemical laws, without the kind of mystery we associate with consciousness. Deep learning uses artificial neural networks that superficially mimic the brain's neural activity. First, an input layer made up of multiple nodes connects to another layer of nodes called the hidden layer. After passing through several hidden layers, it finally reaches a single output layer. This simple network that moves from input to output is called a feed-forward neural network. And since there are multiple layers between input and output, it can also be called a multi-layer perceptron. By now, you might be wondering whether you really need to know all these complex terms. But neural network algorithms are already deeply integrated into our lives in ways we cannot ignore. Some companies have long been using neural network algorithms and may already be evaluating your job application. The company you applied to already has data on the traits of both its low and high performers. For example, foreign language scores, number of job-related certifications, and total number of social media friends, all metrics that may directly or indirectly affect performance. This data becomes the input values. The company also has reports scoring existing employees' actual performance on a scale of 10. This becomes the output value. Now the company can train a program based on this organized data. Here, training means adjusting the neural network's weights so that when an employee's input values are entered, the output best matches their actual performance score. Deep learning doesn't just move forward from input to output, it also moves backward, adjusting weights to continuously reduce the error between the actual score and the score predicted by the neural network. This is backpropagation, the core of deep learning. Also, since the adjustment was based on existing employee data, we can say the computer was trained using a method called supervised learning. We could call this program a performance algorithm. Now, it's your turn. Your information from the job application is then fed into the trained algorithm. Based on your information and the learned weights, the performance algorithm can output a predicted score of how well you would perform if hired. The company's HR manager can then easily decide whether to hire or pass on you based on this output. Although I've skipped many details, this is the basic working principle of deep learning based on artificial neural networks. Now you're ready to think about the controversial topics intertwined with AI. If we ask a machine a question and cannot distinguish whether the answer came from a human or machine, can we consider that machine to have intelligence and consciousness? This is precisely the Turing Test proposed by Alan Turing. Artificial neural networks used in deep learning have evolved and improved to create GPT-3, a program capable of writing at quite a high level. And if this program is developed further, it could potentially reach the level of conversing like a human. Depending on one's perspective, one might argue that GPT-3's current output is indistinguishable from human writing. We once presented this sentence to GPT-3. And upon reading this, it elegantly continued the story with human-like creativity. If we cannot judge whether something was written by a human or a machine based on the quality of the writing, then according to the Turing test, couldn't we conclude that it has intelligence? Of course, judgment varies depending on how we define intelligence, but intuitively we sense that this machine lacks true intelligence. The Turing test sidesteps the question of what intelligence actually is. Even if GPT-3 passes the Turing test, we know it is merely a simple input-output machine. It produces sentences based on combinations learned through neural networks, outputting appropriate responses to questions. GPT-3 doesn't truly understand questions and answer them. It generates statistically probable words in sequence to respond. GPT-3 could potentially pass the Turing test without possessing genuine intelligence. Humans continuously learn through bodily senses and build models of the world. If you want to know how a thrown ball interacts with objects, simply observing the ball is enough. Building a model of the world by understanding cause and effect through interaction differs from deep learning's approach. Based on our world model, we also anticipate what might happen next. Results may differ from our expectations. If throwing an apple shattered a metal block, we would feel something unfamiliar. But if necessary, we readily revise our world model. Even a 5-year-old builds an excellent world model by smashing countless objects with toy cars. We need to create a machine with intelligence superior to a 5-year-old in every aspect. But whether a child's abilities are remarkable or technological progress is slow, achieving this goal remains extremely difficult. To predict a ball's movement, does it make sense to input all relevant data and perform machine learning? If we cannot solve how to present everyday knowledge to computers, perhaps we may never be able to create truly intelligent machines. Another difference between humans and deep learning systems relates to processing diverse models. We discover similarities between games like chess, Go, and Jangi and learn quickly. We can apply one model to another or hold multiple game models simultaneously. Humans can even play chess and Go at the same time. But for AlphaGo, the Go champion, to play chess, it must erase everything it knows about Go and study the new game rules from scratch. Therefore, AlphaGo can never simultaneously possess chess and Go skills that surpass ours. Likewise, no matter how advanced GPT's language abilities are, it would be difficult for it to simultaneously have the skills of a chess grandmaster. When you think about it simply, this seems very strange. Both AlphaGo and GPT-3 are based on deep learning using neural networks, one for playing Go and the other for language. Also, Deep Blue, which defeated a chess grandmaster in 1997, used a game tree algorithm, but it's also possible to play chess using deep learning algorithms like AlphaGo and GPT-3. So all three can operate through deep learning, yet they cannot be integrated into a single system and must run separately. Meanwhile, we can play chess and Go simultaneously while verbally taunting our opponent. Deep learning algorithms pale in comparison to the human brain. Perhaps intelligence shouldn't be measured by how well one performs a single task, but by the ability to flexibly learn whatever comes one's way. Considering all these factors, we can conclude that all AI developed so far actually lacks true intelligence. To avoid misunderstanding, deep learning has certainly shown remarkable achievements in recent years. But the intelligence we're discussing here demands more than just playing the imitation game and passing the Turing Test, as language model does. If we want to go further, we first need to clearly understand the limitations of our current tools. Another problem with deep learning is that we cannot fully comprehend the decision-making process of the neural network. A performance algorithm built on deep learning can notify job applicants of the hiring decision, but it's impossible for us to understand the process behind the result. If a person had evaluated you, you could ask that interviewer why you got such a result. But with an algorithm, only the weights of countless connected networks and functions in nodes determine whether you get hired. It's essentially a black box filled with uninterpretable data. Moreover, deep learning faces significant challenges in real-world implementation due to two major problems. The first is data shift, caused by differences between training data and real-world cases, and the second is underspecification, where multiple models show similar predictions but have vastly different weights, causing confusion about which model is valid. Due to these issues, deep learning cannot be quickly applied to critical fields like healthcare. We still have no choice but to rely on expert intuition and judgment. What's worse is that speculation and marketing hype are extremely common in the deep learning field. Some big tech companies emphasize their massive neural network models, promoting that their deep learning models will soon think like humans. But there is no scientific basis yet to verify such claims. Many big tech CEOs claim that superhuman AI is less than 5 years away, but every new year, they keep pushing back their predictions. Reality is far from their hopes, and it remains uncharted territory that no one can guarantee. Such narratives are enough to plant misconceptions about AI in the general public and actually hinder the advancement of AI. After GPT-3's release in 2020, IT companies began competitively launching language models with massive neural networks. Most are enormous models exceeding GPT-3's 175 billion parameters. South Korean tech company Naver's language model Hyperclover has 204 billion parameters. Megatron Turing NLG, jointly created by Microsoft and NVIDIA, has 530 billion parameters, and Google's Switch Transformer has 1.6 trillion parameters, 10 times that of GPT-3. Large language models produce more natural language than before, but these companies didn't scale their models, hoping for new intelligence to emerge, and they haven't resolved fundamental problems of large language models. It remains unclear whether backpropagation truly mirrors how the brain learns. Does the brain fine-tune itself through forward and backward passes like deep learning, or does it do something similar to supervised learning? If how the brain learns isn't identical to how deep learning works, we may be missing something. Therefore, another camp of AI researchers argues that deep learning has limitations because it vaguely imitates the brain without precisely understanding how it works. Some engineers, recognizing this issue, are researching new neural networks that operate more like actual neurons. As such, deep learning is both the most promising field in AI and potentially the one holding us back. Deep learning may not be the one to fulfill what early AI researchers dreamed of, machines with human-like intelligence, the vision of artificial general intelligence. Although the initial ideas behind deep learning were inspired by how the brain works, It no longer concerns itself with the brain or neuroscience and is seen as pursuing its own path, relying more on mathematics and computer science. Despite much effort, if it turns out that deep learning fundamentally cannot produce genuine intelligence, achieving what we consider true intelligence, artificial general intelligence, will require a new breakthrough. To create intelligence, we may first need to closely examine how intelligence and consciousness arose in creatures found in nature. Meet a creature beloved by neuroscience researchers. It is C. elegans. Neuroscientists do find this creature quite elegant indeed. The structure of C. elegans isn't very complex, so even with our limited technology, we can access its biological information. When we strip away the outer layer of C. elegans, we can see its nervous system wrapping around the muscles. This isn't very interesting yet, so let's remove the muscles too. Now the digestive and reproductive systems appear. These aren't our focus either, so let's remove them. Strip away the outer layer, muscles and organs, and what's left is the neural map of C. elegans. C. elegans entrusts its entire consciousness to these thread-thin strands. If anything, we might call consciousness resides in this creature at all, that is. The neural network of C. elegans consists of just 302 neurons simply connected to one another. As you can see here, we have mapped the entire neural network of this creature and even named each neuron. A map like this, showing every neural connection within a creature, is what we call a connectome. What could it mean for us to know the connectome of this tiny creature? Quite some time ago, engineers ran a fascinating experiment using this knowledge. They replicated the entire neural network of C. elegans in a computer and attached sensors and wheels to it. Without any commands, the device appeared to move on its own. The behavior of C. elegans emerged from the neural connections alone. Although it's a crude machine that merely mimics the neural network, did we actually create a digital life form that thinks like C. elegans? Could the behavior, intelligence, and consciousness of living beings truly originate from neural networks? If so, the fastest path to unlocking artificial general intelligence might be to turn back to ourselves and map the human connectome rather than rely on vague imitation. But as you can imagine, completing a human connectome is no simple task. Humans have 86 billion neurons, and the connections between them exceed 100 trillion. Mapping the human connectome is an entirely different story from C. elegans. Is it possible to map all 86 billion neurons and 100 trillion connections? Neuroscientist Henry Markram has said it is possible. The Human Brain Project, or HBP, aims to map and simulate the connections of the human brain. It has already begun in Europe and is currently underway. But this project has been facing challenges just as massive as its ambitious plan. The HBP, in its scale and purpose, reminds us of the Human Genome Project, HGP. The HGP, which ran from 1990 to 2003, was a long-term project aimed at acquiring all human genetic information. At the time, many steadily questioned its practicality. However, thanks to the HGP, we ultimately gained a deep understanding of our species. Furthermore, it enabled us to understand and treat genetic diseases. The HBP will most likely fail to simulate the human brain. But this won't be the end. Rather, it's likely to become a starting point for understanding our intelligence and consciousness. Yet questions still remain. If the initial vision of the HBP, simulating the human brain in real time, is someday achieved, could we truly create something with genuine intelligence? Let's be clear about one thing. While the brain is certainly a physico-chemical device, there is no guarantee that consciousness will emerge when this physical network is recreated in a computer. Therefore, let's add one assumption and proceed with our final discussion. That is, if we complete the connectome of the human brain and implant it into a machine, we could create a machine with intelligence and consciousness. Why do we imagine and want to create machines with intelligence? Of course, robots with artificial general intelligence would offer many advantages. Intelligent robots could endure the harsh Martian environment, far too hostile for humans, constructing buildings, growing plants, and awaiting humanity's arrival. But beyond practical considerations, the reason we imagine artificial general intelligence may be to gain philosophical insights into what makes us human through the process of trying to create machines that resemble us. We always learn something from experience, apply what we've learned elsewhere, and accomplish various tasks simultaneously. These are the human qualities that make you and me superior to current AI. What if technology advances to create machines as intelligent as us, or even far beyond us? Imagine machines with high intelligence and immense computing power discovering the final theory unifying quantum mechanics and gravity, or solving every challenge facing humanity. It brings catharsis, but also fear. But no matter how advanced AGI becomes, a machine with superintelligence surpassing humanity in every aspect may remain purely imaginary. As mentioned earlier, for a machine to have intelligence, it likely needs to perceive the world as humans do. Jeff Hawkins, founder and scientist at neuroscience company Numenta, points out that an AGI that gains consciousness by emulating the human brain must interact with the world on the same physical timescale as humans. Such a machine would likely have a slow learning process. Moreover, the world constantly changes and our perception adapts and expands accordingly. Therefore, a machine superior to humans in every respect may be difficult to achieve. These ideas might be somewhat disappointing. If the singularity we've imagined doesn't exist, what should be the ultimate vision for artificial general intelligence? The basic goal of every living being is to preserve its genes. But if humanity can no longer survive biologically, what should we strive to preserve? Jeff Hawkins says what we should leave behind is human knowledge. Machines with artificial general intelligence may be the strongest evidence that humanity once existed in this universe and cultivated a magnificent culture, and perhaps the final beacon of intelligence illuminating the cosmos.